what does it actually mean for a machine to learn? We understand how a human brain adapts to new information, but a computer has no organic intuition. To make a machine learn, we have to invert the logic of how we program it. For decades, software development followed a rigid manual process. A human developer had to supply the computer with raw information and write the exact step-by-step operational rules for what to do with it. This traditional method follows a simple equation. You input data, write algorithms, and output results. Machine learning rearranges this. We give the computer raw data and expected results, and the machine figures out the algorithm. By moving the algorithm to the end of the equation, computing changes from an exercise in human calculation to a process of autonomous machine discovery. The machine identifies the rules that connect the starting point to the finish line, but a computer cannot discover these rules in a void. To figure out complex algorithms on its own, the software requires a specific physical and logical architecture. This architecture operates across expansive physical and logical dimensions, ranging from microscopic, single operations to massive, multi-layered digital structures. As data moves through this structure, the software alters its own internal pathways. It tests connections and reroutes itself to learn from mistakes. To understand how this works, we are going to map this architecture from the ground up. We will isolate the absolute simplest foundational node before attempting to understand the complex whole. Breaking AI down to its simplest individual component is the only way to demystify complex black box systems like deep learning. To build an architecture capable of learning, computer scientists looked at the cellular structure of the human brain. This biological model became the blueprint for what we call neural networks. In a biological brain, neurons constantly send messages to one another. When solving a problem, the brain strengthens the connections that lead to success and diminishes those that lead to failure. When we translate that biological process into a computational model, the organic network snaps into a rigid mathematical grid. At the center of this grid is the foundational unit of all modern artificial intelligence, a single node called the perceptron. The anatomy of a perceptron is simple. It has exactly one input path and 0 hidden layers. Because of this structure, a single perceptron is only capable of making one simple decision based on the raw input data it receives. While a single perceptron has limited processing power, it forms the bedrock computational atom of all modern artificial intelligence. To handle tasks that require more than one simple decision, individual perceptrons are networked together. This is a multi-layer perceptron. When developers use the term neural network, they are referring to this 3-layer architectural layout. The first stage is the input layer, represented by this vertical column of yellow nodes. The perceptrons in this layer act as the entry point. They make initial binary decisions based on the raw data entering the system, then pass those findings forward. Those initial findings travel to the second stage, the hidden layer, marked by these blue nodes. The blue nodes do not look at the raw data. Instead, they mathematically weigh the results passed to them from the yellow input nodes. This internal weighting process allows the network to process information at a higher level of abstraction. Finally, the hidden layer sends its data to the output layer, represented by this red node. This final node synthesizes the work of the hidden layer to deliver the final processed result. Linking these 3 layers allows a machine to abstract raw data into a reasoned, logical conclusion. A standard 3-layer network is effective for basic logic, but when processing massive visual datasets, the system hits a bottleneck. It lacks the internal depth to analyze millions of pixels simultaneously. Deep learning is the architectural solution to this problem. We achieve this depth by inserting multiple successive hidden layers, shown here in green, between the blue and red layers. In these networks, each successive layer must use the output of the preceding layer as its own raw input. We see this in optical character recognition, how a computer reads a scanned letter. Raw pixel data feeds directly into the yellow input nodes. The blue nodes activate, processing the pixels to isolate the hard geometric edges. These lower layers only process basic, low-level physical traits because they are closest to the raw input. As the data moves forward, the deeper green nodes activate. They mathematically combine those isolated edges into recognizable shapes. These deeper layers synthesize abstract human concepts from simple geometry. The final red node then activates, outputting the recognized letter in a clear, readable format. Deep learning functions as a massive chain of basic perceptrons, dividing a complex problem into thousands of tiny, layered decisions. In technical contexts, machine learning and deep learning are often treated as interchangeable, but they have distinct structural definitions. Deep learning is a specialized subset residing within the broader machine learning category. As this grid shows, standard machine learning functions on smaller datasets. Deep learning requires massive datasets to function effectively. Consequently, machine learning generates simple algorithms, while deep learning produces the complex algorithms required for tasks like image recognition. A software engineer chooses the structural depth based entirely on the complexity and scale of the available data. This leads to the final dividing line between these systems, the threshold of autonomy. Traditional machine learning models often require humans to guide and train them. Deep learning models possess the architectural depth to learn and iterate entirely on their own. This capability is the result of the architecture we have mapped, from a single perceptron to an autonomous, multi-layered deep network. Modern artificial intelligence is an architecture designed to ingest data, analyze the results, and autonomously build the rules connecting them.